Hello. So, I'm always saying understanding is more important than memorizing in math. One thing that we're taught just to accept on faith is the number e, which is about 2.72. But we're not really told what e is. The purpose of this video is to start down that rabbit hole, like what is e. I think e was actually invented studying money, like interest, like continuously compounded interest. So the way I'm going to teach what E is not really how it was invented. But anyway, let's go. So we're trying to basically develop a theory of the number E. All right, so here I have a graph of 1 over x. Let's begin by defining, so our ultimate goal is to define E. To that end, let's begin by defining log x. Now I know in high school, when you see this, your teacher says that means log base 10. In higher math, when you see log though, it frequently means log base e. In other words, what you've learned is ln. So I'm going to adopt that here because we're doing higher math. So when you see log with no base in this video, it will mean log base e. So we're going to define this log base, we'll just call it log. We're going to define log x as the integral from 1 to x of 1 over t dt. So notice this axis I've labeled t. I didn't know what to label this axis, so I labeled it y. And then instead of e to the x, we'll just, because that looks like we actually have a number called e and we haven't really defined what that is, we'll write exp x, which means e to the x. So exp x is the inverse of log x. That's how we'll be defining it. Well, we know that we want this property for exp. That's hard to say. We know we want this property to hold, right? We want exp a times exp b to be exp a plus b. I was trying to prove that. So, I've said before in my proofs, I do them backwards. I start with my goal and then I massage my goal until I get something obvious with this symbol, which means is equivalent to. And I couldn't really make headway with that. So I decided, well, let's do an analogous property with logs. We have a hunch that this is the analogous property with logs, right? Log m plus log n equals log mn. So my proof of that was, looking at this picture. Again, I go backwards, and then we'll unpack this. So this is the integral from 1 to m. This is the integral from 1 to n. And this is the integral from 1 to mn, right? We need to show those are equal. So I'm going to pack these. So the integral from 1 to m is the limit as n approaches infinity. So we're going to do like a Riemann sum. So we're going from 1 to m. So assuming that m is greater now, just for visualizing, the distance between 1 and m would be m minus 1. I divide that into n pieces, and then my function is 1 over. So I start 1 over 1 is like my left endpoint, because I'm doing the rectangles. This is my width, the width of my rectangle, and the height will be 1 over my x or t coordinate. So my first t coordinate is just this 1, and then I've got to do some i's, and this is like my width of my rectangle, and I'm counting from 0 to n minus 1. So that's a limit. Then this limit is easy to do once we've done this one because it's analogous, right? So this is an m instead of an n. This is an m. Instead of an I, I'm going to use a j. This will be a little m. And then this is an n as in November, right? This should be the same except for we've got a j here instead of an I, and this is an n, big N as in November instead of a big M as in Mike, and this is a little m as in Mike instead of a little n as in November. And we've got our equal sign. Then we'll unpack this in an analogous fashion. So let's see, we're going through the alphabet here. So we've used n as in November, m as in Mike. We'll use p now because it's sort of the next letter. Oh, it looks like a 0. So p, I, j, k. And then we'll take p minus 1 of them, right? Because rectangles we would only go from p minus 1, because like as a computer scientist, we start counting at 0, like computer scientists do. So this is Mike times November up here, because we're going all the way to Mike times November. 1 over 1. Notice instead of a j here, I have my k. Instead of my November, I have my Mike times November. And instead of my little Mike, I have a little p. All right, now this is, again, my proof technique I frequently use. I go backwards and I use these double arrows. So I'm trying to prove that in math is a lot of copying. So I copy this, I copy that, I've copied this. Now, what did I do here? I'm multiplying numerator and denominator by little n as in November, right? This is n, this is n. Okay, and then I don't really know what to do here, so I'm going to stop this video. Maybe it'll take a few days to percolate. Maybe eventually I'll figure out how to develop this further, but this is some nice insight about how one could go about developing a theory of the number e. I'm going to stop this video here.